Hey guys, Dean Chase here with another geometry lesson for you. Hope you all are doing good. Let's get this thing started with a word of prayer. Dear Heavenly Father, I want to thank you for this day you give us, Lord. I want to thank you for all you do. I want to thank you for all my students. Please help us continue to learn and grow in knowledge. We love you. Amen. Alright guys, so today we're going to be covering lesson 2.6 and we're going to learn how to prove statements about segments and angles. This is page 112 if you're following along in the book I'm teaching out of. So, let's go. A proof is a logical argument that shows a statement is true. There are several formats for proofs. A two-column proof has numbered statements and corresponding reasons that show an argument in a logical order. In a two-column proof, each statement in the left-hand column is either given information or the result of applying a known property or fact to statements already made. Each reason in the right-hand column is the explanation for the corresponding statement. So we've kind of already been doing two-column proofs with last lesson because that's the way I like to just start teaching it. The only difference is now we're going to be numbering each step, whereas last class we didn't number each step. So here's your concept summary of writing a two-column proof. So for your notebook, writing a two-column proof. In a proof, you make one statement at a time until you reach a conclusion. Because you make statements based on facts, you are using deductive reasoning. Usually the first statement and reason pair you write is your given information. You guys know that. We did that last class. Here's an example proof of the symmetric property of congruence. They were given that angle 1 is congruent to angle 2, so they wrote that. And then they needed to prove that angle 2 is congruent to angle 2. And they did it with this proof. This is actually a theorem we're going to learn today. And this is the proof of why that theorem is true. Like it said before, the left-hand side is statements based on facts you know or on conclusions from deductive reasoning. And then the right-hand side are either definitions, postulates, or proven theorems that allow you to state the corresponding statements. Okay? How long each proof is will definitely vary. Today we got a really long one, so just buckle in and enjoy the ride, you know? So our first proof is actually one we've already done before in last class. So this one shouldn't be that different from what we did before. So let's just get started. So we're given that RT equals SU, okay? They want us to prove that RS is equal to TU. So the first thing we're going to do with this is we're going to just state our given statements. That RT equals SU. Notice the difference between the last time we did this and this time is there's just a 1 in front of the RT equals SU. And our statement is, our reason is still the same, and that's given. And we also number this side. Okay, so last time we did this, we wanted to say that ST is equal to ST because the ultimate goal is to subtract this section to show that these two sections are the same. So ST equals ST. And the reason for that is the reflexive property of equality. Because anything is equal to itself. Now we are going to, we can subtract ST from RT and we can subtract ST from SU, and that'll leave us with our RS and TU. And we're allowed to do that because of the subtraction property of equality. Okay, so now what they're going to want us to state is what RT minus ST equals. RT minus ST. And also, so what does RT minus ST equal? It's going to leave us with RS. So we're just going to say that. RT minus ST equals RS. And the reason we're allowed to do that is the segment addition postulate. I know that can actually be kind of confusing because we actually did subtraction here, but Segment addition postulate just says two segments make up a different segment. Okay, so two segments are making up a different segment. So now we need to decide what SU minus ST equals. SU minus ST. And that is going to equal TU. Do you see what we're doing here? We got our RS and TU, the two things we're trying to prove. Now, we have, I'm going to underline the SU minus ST in red, and that's equal to TU, okay? You don't have to underline and circle things in your proofs. I'm just trying to explain this better. Then we have RT equals RS. So we have that RT minus ST right there. So what we can actually do is take and substitute in our RS for this RT minus ST, because we said that's what it equals. And we can substitute in this TU for SU minus ST, because that's what we said it equals. Oh, sorry. We're rushing ahead. What was the reason for statement 5? The same as statement 4, the segment addition postulate. Okay, now let's substitute in our RS and TU. So we're going to have RS equals TU, which is going to be what we're trying to prove. And the reason we're allowed to do that, I use the word multiple times, we're substituting it in, okay? So the substitution property of equality. Yeah, example 1. We kind of already done that once before, so I just hope it reaffirmed your knowledge in it, and let's keep going. Theorem. The reasons used in a proof can include definitions, properties, and postulates, and theorems. A theorem is a statement that can be proven. Once you have proven a theorem, you can use a theorem as a reason in other proofs. So, Theorem 2.1, congruence of segments. Segment congruence is reflexive, symmetric, and transitive. Okay? So you're allowed to use reflexive property for congruent segments. So if, for example, segment AB will be congruent to segment AB. Symmetric, where we flopped it over, if segment AB is congruent to segment CD, then you could also say that segment CD is congruent to segment AB. And the transitive property, if segment AB is congruent to segment CD and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. It's like the law of syllogism. Remember that? We learned about it a while back. I'm going to keep saying it probably. Transitive property. And the same goes for congruence of angles. So angles can be reflexive, symmetric, or transitive also. So I'm not going to read all that again. It's pretty basic. Make sure you put it in your notes, and let's keep going. So name the property illustrated by each statement. If angle RST is congruent to angle MNP, then angle MNP is congruent to angle RST. What happened there? It looks like we just flopped them around, right? Where MNP is now first and RST is now last, which means that would be the symmetric property of angle congruence. Okay, let's do this one. If segment AB is congruent to segment FG, and FG is congruent to MN, then AB is congruent to MN. So here we have two FGs congruent to two different things, and then they say those two different things, segment AB and segment MN, are congruent. What property says that we can do that? That would be the transitive property of segment congruence. Not bad, right? Geometry, so much fun. Who knew, right? Let's keep going. If you know that M is the midpoint of AB, segment AB, N is the midpoint of segment CD, and AB equals CD, prove that AM is congruent to CN. Okay, so we're ultimately trying to prove that this little section is congruent to this little section. And the first thing we're going to do is let's go ahead and write our givens down. Okay, so there's 3 givens. I actually wrote them in different steps. You don't have to do that. They could all be step 1, or It can be through step 3. It's really up to you. I just, for the sake of like organization, labeled them differently. So M is the midpoint of AB, which is given. N is the midpoint of CD, which is given. And AB equals CD, which is given. So we know that AB, this whole length, equals CD. And we know that M and N are both the midpoints. So that means those two segments are cut perfectly in half. So like you're probably just thinking, they're equal because they're cut perfectly in half and the whole lengths are the same, so their half lengths will be the same. I wish it was that short, but it is not. The first thing we're going to do is state what it means for M to be the midpoint and what it means for N to be the midpoint. So what that means is that AM is congruent to MB, right? So I'm going to mark that here. AM is congruent to MB. We also know that CN is congruent to ND. I forgot to write the last given. So we're going to write those down. AM is congruent to MB, and CN is congruent to ND. Okay? And the reason we know that is a midpoint, right? A midpoint says that two halves will be equal if it splits it. So the definition of a midpoint, okay? Here we're using a definition. A lot of times my students will ask me like, oh, what are we supposed to write for this? I'm like, well, you tell me what it is. And they'll be like, well, it's the midpoint. So the definition of a midpoint, okay? So now that we know that, we know they're congruent, where they want to work with, they're equal to each other from here on out. So if you know these two segments are congruent, if you know this is congruent and this is congruent, we could also say that they're equal to each other. So AM equals MB and CN equals ND. Okay, and the reason for that is the definition of congruent segments. Okay, another definition. Now, what do we want to do? I think we are going to want to say what AM plus MB equals, okay? And we're going to want to say eventually what CN plus ND equals. So let's go ahead. AM plus MB equals what? AB, okay? And why do we know that? Segment addition postulate. Okay, and we're going to do the same thing for CN plus CD plus ND equals CD, and that's also the segment addition postulate. Okay, now here is where it kind of gets a little tricky. Here's the thing about proofs. I'm gonna go ahead and just throw this out there. A lot of my students are like, how am I ever supposed to like know that's what the next step should be? And the way you do it, proofs are a lot of just watching. You watch, you read them, and then you're like, oh, that was the logical order they did that. So what I always tell my students, write my proofs down, but also go back and look at the examples in your book of proofs and just continue to read them. Because the more you read, just like history or anything else, you soak it in. But here it's more like logical. I compared it to like how residents will watch surgeries. And you just keep watching and watching, and then you develop the steps to do that surgery yourself. Anyways, that was a rant. So we're going to take this here, and we know that AM plus MB equals AB. We also know that AM equals MB. So we're actually going to substitute in for MB another AM. Okay, so AM plus AM equals AB. You see, we're getting closer to being able to just have a, because we know that AB equals CD. AB equals CD, okay? So we're trying to eventually substitute in AM for AB and CN for CD. And we're getting kind of close, okay? We're going to do it again for this step, CN plus ND. We're going to substitute in another CN. And that was a substitution property of equality. My bad. CN plus CN equals CD. Also the substitution property of equality. Now, in algebra, if you have two of the same numbers, or like this was x and this was x, you could call that 2x, right? we can actually call this 2AM equals AB and 2CN equals CD. I'm going to go ahead and throw that in one step. And the reason for that is the distributive property of equality. Okay? Next, we can say, because we know AB equals CD, right? AB equals CD, AB equals CD. We can actually substitute in 2AM equals 2CN because we have AB and CD. And that would be the substitution property of equality. Okay? The last step, substitution property of equality. And the last step, we can take the 2's away. Because if we divided each side by 2, that would remove the 2's, right? So, AM equals CN. And the property we used was the division property of equality. Wow, that was long. But also, it's a ton of good information to be learning how to logically form other proofs in the future, okay? Because I'll admit, it's hard to kind of get these steps flowing, but once you get that logical thinking, you'll start flying through these examples. Okay, example 4. Okay, I'll read the question first and then we'll go ahead and start working this out. The distance from the park to the pool is the same as the distance from your house to the school. The school is between the pool and the house. Prove that the distance from the park to the school is the same as the distance from the pool to your house. So, the first thing I'm going to say here is like we definitely have to draw something to be able to figure this one out. So, I'm going to put my dots here, connect them all with a line. So, it says that the school is between the pool and your house. So, this is going to be school, house, pool, park. Okay? The distance from the park to the pool is the same as the distance from the pool. Yes, okay. So just making sure I had those in the right order. Okay, so next thing, to make this easier so you don't have to keep writing the full words like park, pool, school, house, we're going to actually assign them letters. So this is going to be A, this is going to be B, this is going to be C, and it's going to be D. And here you can see we're just going to start messing with segment lengths, okay? Well, the given information is the distance from the park to the pool is the same as the distance from your house to the school. So AB equals CD, right? Park, pool, school, house. So we're going to go ahead and write that down. And the reason for that is it's directly given, okay? So we're trying to prove that the distance from the park to the school is the same as the distance from the pool to your house. So park, school, pool, house, okay? Well, this is a lot like our first example. So if we look here, we have this section that is shared by both, right? I wonder, let me do this. I'm gonna give this a shot. We're trying to prove park, school, okay, is the same as pool, house. So if you actually look, they overlap from here to here, okay? Which means that that is the same distance. They're overlapping. Well, we know that these two sections are the same because that's given to us in the beginning. So somehow we have to figure out how we're going to remove that middle section logically to make sure we don't like just throw random things out there. So I'm going to suggest we take and set BC equal to BC so we can remove it from each side of the equation. And the reason we know BC is equal to BC would be the reflexive property. Okay, now we can take and we can add BC to each of these, right? So let's go ahead and add BC to each side. AB plus BC equals BC plus CD. And that would be the segment addition. No, sorry, the addition property of equality. My bad. because we added the same thing to each side of the equation. That is the addition property of equality. Now is where we're going to use the segment addition postulate. And what we're going to need to do is we need to say what AB plus BC equals and what BC plus CD equals. Because if you look, AB plus BC, that's the park to the school. And then BC plus CD is the park to the house, which is what we are trying to prove. So AB plus BC equals AC, park to school, okay? And that would be the segment addition postulate, okay? Now we want to know what BC plus CD equals. BC plus CD is going to equal BD, which will also be the segment addition postulate, okay? Now we know that AB plus BC equals BC plus CD, right? AB plus BC and BC plus CD right here. We know those two things are true, and we're trying to prove that AC equals BD. Well, if we look, underline, underline, AB plus BC, both those are equal to AC, right? BC plus CD equals BD. So we could just substitute these back in to this equation, and we're going to be left with AC equals BD. And what did we do? We substituted it in. So it's the substitution property of equality. Guys, that's your lesson. It's not too bad. I hope it made sense. Thanks for following along. As always, have a good day. See ya!